Hello, and welcome to the Ultrasound Physics module. Now, in the next series of talks, we're going to be diving into the world of ultrasound physics. Before we get started in today's talk, I want to make sure we have a clear concept of what exactly a sound wave is and what it isn't. We'll start by having a look at a definition. Now, sound is mechanical energy that propagates through a continuous elastic medium by the compression and rarefaction of the units in that medium. So, let's break down this definition a little bit more. It's mechanical energy. It's not self-propagating energy like in all electromagnetic radiation. It requires a mechanical force. When we are creating sound, we are mechanically moving our voice box. When we create ultrasound waves, we are moving an element within that ultrasound. And that energy propagates through a medium that needs to be continuous. Sound needs a medium to propagate. When we look at electromagnetic radiation, it could travel through a vacuum because it's self-propagating. Here, sound is dependent on a medium. And if that medium is not continuous, if there are regions of vacuum within that plane, the sound will not propagate. Secondly, the medium needs to be elastic. Now, what does that mean? Well, the molecules or the units within that medium need to be able to move, transfer energy, and return back to where they started. If I had my hand in some water and I pushed the water, the molecules that I initially pushed will then return back to where they were, and a wave will propagate through that water. If I had a pile of sand in front of me and I pushed the sand like that, a wave wouldn't propagate through that sand. The sand that I pushed wouldn't return back to its resting place, and we wouldn't get that transfer of energy. The sand has no elasticity. We'll look in later talks at the elastic and inertial properties of a medium and how that affects the speed of the wave traveling through that medium. So when we look at a wave, we can see its regions of compression and rarefaction. These regions of compression and rarefaction represent localized pressure changes within that medium. We can plot those pressure changes on a graph, and we get a sine wave. Here the regions of compression have high localized pressures, and the regions of rarefaction have low localized pressures. We can plot these with the x-axis being the normal pressure within the tissue. Now in practice, the amplitude of compression is actually higher than the amplitude of rarefaction. But for practical purposes, we will represent a sound wave like this within the talks. And you'll see that in textbooks as well. Now the energy here is transferring from left to right, but the molecules are not moving all the way across. They are staying in the same place, oscillating back and forth. When I'm speaking to someone, the air molecules leaving my mouth is not the same air that is reaching someone's eardrum. There the energy has passed.